Hey, my name is Catherine. I'm an SRE in finance and also extremely pregnant. And I'm going to talk to you tonight about the mathematics of origami. And this subject is like really hard to visualize. So I have this huge stack of spacey origami paper. I encourage you to come get one if you think visually and spatially.
I'll grab it and pass it around.
Okay, could I just take one? Yeah, I'm going to need one too.
Everyone to come flooding up.
Okay. So, no, it's super cheap. It's paper. It's like a penny on Amazon. So one of the things that happened when I got pregnant is that my parents immediately started scanning photos of me when I was a child, in an effort to see like what my baby would look like when it's outside. And seeing this photo of myself with my Uncle David made me think that now that I am an adult and able to understand calculus and have a rudimentary understanding of CS theory, I should really go back and look at his work. So the thing he's really famous for is Huffman Coding. It's a compression algorithm used in JPEG and many other data formats. He invented this as part of his graduate work at MIT. His graduate homework, to be specific. It wasn't a specific research topic. And then in the 70s, he got involved in some good old-fashioned AI approaches. What they were trying to do was scene analysis. So in the 70s, we had pretty good algorithms for detecting edges in pictures, but we had no way of telling like what is actually in the picture from the edges. So one idea was that, well, determining how three-dimensional polygonal structures project onto a 2D space is just a computational geometry problem. And if we understood everything that we could possibly understand about computational geometry, then we could just figure out what the shapes of pictures are from their edges. And this is actually an incredibly challenging problem, and it's much easier in the modern day just to throw a lot of compute power at it. But it was a valiant effort. So this paper led him into origami, because if you think about it, origami is kind of like a version of the scene analysis problem. You have this two-dimensional material that has very nicely defined lines, and it transforms into a three-dimensional structure. So I think because of his work in that, he started getting really into looking at origami, and this is the paper that I'm going to be talking about tonight in 1976. And after he did this paper, he didn't really publish anything else. He invented a lot of really cool origami sculptures, and growing up, a lot of my family members had these sculptures in their houses. There's a computer scientist and his father at MIT named Eric and Martin Domain, who have worked with my family and talked to my uncle right before he died to try to get all of his knowledge and be able to reconstruct his sculptures. The two sorts of sculptures that he made were these tessellation patterns, where you basically just repeat the same straight creases over and over to get a sort of flat but three-dimensional structure. And he also did a lot of work generating curved patterns. So the way that we analyze what is possible to make out of paper is using Gaussian curvature analysis. So the thing you have to know about paper is that it's not spandex. You cannot create more paper in general by stretching the piece of paper. And stretching the paper will change this parameter called the Gaussian curvature. This leads to two different classes of surfaces in general. One is called a developable surface, which is generally what paper is. So with a piece of paper, you can make a cylinder, you can make kind of a cone structure and kind of a spiral structure, but you can't easily make a sphere or a saddle or a weird vase that has a different size radius. the way that you actually calculate this is it's the product of the radii along two perpendicular axes. So in your saddle structure, you have one value that represents the curvature along this axis, and then you have one curvature that represents the curvature, the radii of curvature along this axis. And so in this surface, k is non-zero, but on a piece of paper, it's going to be 0. And you can try this for yourself. It's impossible to take a piece of paper and have a radii of curvature in two perpendicular axes. And the Gaussian curvature has nothing to do with how bent the paper is. It just has to do with the amount of curvature in two axes. So the way that you analyze how much curvature there is on a piece of paper is using a contour integral. And this is extremely similar to Gauss's law. Gauss was extremely prolific, and this is another thing that he invented. I was a physics major in Canada, and so I am very aware of this because the Physics Student Society wanted to serve beer at their parties, and they wanted to exclude anyone who was under 19, that was the drinking age in Canada, and also all of the engineering students. And Gauss's law is something you learn in like third year electromagnetism. And basically the idea is that if you take an electric field or a point source or any sort of charged surface and you wrap a simpler surface around it, you only have to calculate the total flux through that surface in order to know the total charge of your electric field or your charge. And so what we would do is we would invent a really tough looking parametrized electric field, and we would say, in order to get access to the free beer, you must solve this and tell us how much charge there is in this structure. And the engineers and the first and second years would then pull out like a three-dimensional integral and try to integrate over the thing. And the upper years would just say like Gaussian pillbox or Gaussian like sphere, and then they would get let in. So this problem is very similar to the idea of trying to find the amount of curvature on a surface, in that we're taking a really complicated surface and we're using a contour integral to turn it into a much simpler surface. So the way you can think about this is that we're going to go around, so I'm going to talk about vertices, and just to demonstrate what a vertice is, I'm just going to make like the simplest fold ever with one hand, so it's going to be terrible. But anyway, here's some folds. This is the vertex of the fold, and these are the creases. So what we really want to know is the Gaussian curvature right around the center of this vertex, and that will tell us basically whether it's possible to fold the paper into the vertex that we want at this point. So this is the point P on this surface here. We're just going to trace around and look at all of the normal vectors at each spot on the surface and project them onto a sphere. And the area that is traced out by these normals on the sphere is directly proportional to the Gaussian curvature. So it's still kind of hard to visualize and talk about vectors on a sphere and how they relate to the contour that we're tracing. And so the paper talks about two different types of angles that make it kind of easier to visualize. So the first is the sectoral angle. So the sectoral angle is when you take the paper and fold it flat, that is going to be the angle between the creases. So in mine, I've kind of like haphazardly done this, but they're roughly 90 degrees between the creases. And if you imagine you had a cube structure, those angles would also be 90 degrees. And when you project this onto the Gaussian surface, these angles end up being the angles, the interior angles in the shape that you trace out. There's also this concept called the dihedral angle, which is the angle between the planes. So if I had a piece of paper here, the dihedral angle between this plane and this plane is like 90 degrees. And on a cube, it would also be 90 degrees. And when you project this out, it means that to trace from the normal on the plane A to the normal on the plane B, we have to go 90 degrees on the sphere. The center of the sphere. Sorry, I'm just like hard to draw in 3D with Google Drive. They're drawing. Anyway, so let's look at what this looks like for some pretty simple folds. So if we take a piece of paper and we just fold it in half, as we fold the paper, the normals are spreading out, but because there's only two of them, our trace is only a single line, and the area ends up being 0, therefore the curvature is 0, therefore this is a valid way to transform paper. If we imagine we have a surface with 3 creases, we start off all pointing in the same direction, then as we pull the center of the pyramid, or this triangular shape, up, the normals are going to spread out and go apart from each other, and we're basically going to get a spherical triangle that increases in area. And because we have non-zero area here, we know that this is not a possible surface that you can create out of paper. And in fact, it's not possible to create any surface with only 3 creases out of paper. When I first read this in the paper, I was like extremely skeptical of it, but I encourage everyone to try with their own piece of paper to make a vertex with only 3 creases, and you will probably end up making a vertex with 6 creases. But good luck. You might be able to like bend the paper too, or stretch it out. And then if we have 4 creases, like this fold and then a fold that I've created, as we fold the paper more, the 2 normals on the concave sides here will start pointing across from each other. So this will produce a figure 8 on our Gaussian sphere. And because we're creating a figure 8 and we're tracing, it means that 1/2 of the trace is going to be in a counterclockwise or clockwise direction, and then the other will be in a counterclockwise direction. And the important thing to know about contour integrals is that the direction that you trace matters. So the area in 1/2 of the figure 8 will effectively cancel out the area in the other half of the figure 8, or at least one of the wings is going to be negative. So for valid flat planes, the area in, or the triangle traced out in 1/2 of the figure 8 is going to be exactly the same size as the area traced out in the other half of the figure 8, and they're going to exactly cancel each other out. And the value of E, which is excess angle, but I'm not going to go into that tonight. The more area there is in E, the more bending of the paper. So one of the results that David Huffman found was a relationship between the dihedral angles and the sectoral angles for the simplest possible curve you can make, or simplest possible crease you can make with with a vertex like this with 2 folds and 4 creases in it. So the ratio between the sectoral or the dihedral angles between opposite things must follow this relationship, and the other 2 must follow this relationship with the sectoral angles. Just to remind you, A, B, C, and D are the angles on this piece of paper between the creases. And the angles MN and P and Q are the angles between the planes when you fold it. He also generalized to a vertex with any number of creases and showed that this analysis was also valid. He talked also about tessellations. So a bit later, someone formally started describing these things, but it's basically you take a 4 crease vertex and you just repeat it over and over and over again. And the interesting thing is that even though the piece of paper itself is not developable and could not have a non-zero Gaussian curvature, the piece of paper with all of these tessellated curves can have all sorts of different K values. And this is really useful because there's a lot of materials in material science that we can't bend or stretch or create more of, but we would like them to be in all sorts of curvy materials, like building materials, solar panels, PCBs, that sort of thing. So the result he found here is that if you don't want your resulting tessellation to have a Gaussian curvature, all of the normals must be in the same equatorial plane in your Gaussian sphere, and the tessellation creases you pick out must balance each other out. So they must be positive L from the mid-plane on the Gaussian sphere on one side and negative L on the other side. And this is kind of boring because, I mean, you want to have Gaussian curvature, but I mean, it tells you that if you want to have some sort of interesting curvature in your piece of paper, just make the normals not in the same plane. He also then started to try to talk about curved creases. And so the way that he approximates curved creases is by just moving the trace so that it encompasses two adjacent vertices. So basically you take a curve and you basically just kind of polygonize it or turn it into a bunch of small straight segments. And the interesting result here is that if you want a curved crease that lies flat ultimately, all of the points along the curve that you analyze, they must go through the same central point Q here. And at the end of the paper, he says that he has some ideas about the relationship between the depth of the crease and the angles that you are able to create out of the curved crease. And he's going to write a future paper about this, but he never did. So, and since then, we also haven't found any really good explanations for the sort of boundary conditions and limits on what sort of curved creases are possible, the same way that we have for a simple vertex with 4 creases. And there's an awful lot of other NPhard problems in origami. So for example, a lot of origami is expressed in these crease patterns where they use one color to indicate convex folds and one to indicate concave folds. And it's very difficult to look at a given crease pattern and determine whether you can actually fold it. Another interesting thing was, can you take a given sort of stick figure and construct it using paper, which is like the primary thing that really people who really like origami want to do. They want to create new crease patterns out of figures. And figuring out whether you can construct the thing that you want to make out of paper is also quite challenging. And there's an awful lot of use of curved folds in architecture and design of furniture. For example, think of like any sort of Frank Gehry building. But up until about a decade ago, most CAD problems did not allow for designing curved folds. And even then, all we have for really approximating curved folds is to polygonize it and then use this approximation algorithm on top of it to try to smooth it out. All right, that's all I have to say about this. Thank you.
We've got time for maybe 2 questions if they're quick. If people have questions. Oh, did I see one? No? Or people are? Okay. Just go ahead and say it, and I'll repeat it for the. We'll repeat it for this.
Is there somewhere we can go to learn how to make those tessellations?
Is there somewhere we can go to learn how to make those tessellations?
So on Eric Demain's website, he has a paper where he talks about going through my uncle's notes and recreating them, and maybe that will be useful to you. I am extremely, I don't know, I'm just not very talented when it comes to making things with my hands, so I have all of my attempts have been really ugly.
These slides are going to be online as well?
Yeah.
Okay, then you can get the name obviously from there. So we'll call it there. Thank you. It'll take a few minutes to switch over mics and such, so go get some more pizza, beer if you want it, that kind of thing. Thank you again.